Harvesting solar energy from the infrared light spectrum. Solar energy is one of humanity's most promising renewable resources, yet today's solar panels capture only a fraction of the sun's total output. Conventional photovoltaic or PV cells primarily convert visible light into electricity, leaving vast amounts of energy untapped, especially from the infrared or IR portion of the spectrum, which accounts for nearly half of all solar radiation reaching Earth. Scientists and engineers are now racing to unlock this hidden reservoir of power, developing innovative materials and devices capable of harvesting energy from infrared light. Infrared light lies just beyond the red end of the visible spectrum, with wavelengths longer than 700 nanometers. Unlike visible light, infrared radiation carries less energy per photon, making it harder for traditional semiconductors such as silicon to convert it efficiently into electricity. Standard silicon solar cells have a band gap of around 1.1 electron volts, meaning they cannot absorb photons with lower energies, essentially allowing most infrared light to pass through unused. Overcoming this limitation requires materials that can respond to lower energy photons while still generating a usable electric current. One of the most promising frontiers is quantum dot and perovskite technology. Quantum dots, nanocrystals made from semiconducting materials, can be engineered to absorb specific wavelengths, including the infrared range. By tuning their size and composition, researchers can design quantum dots that efficiently harvest lower energy photons that silicon cells miss. When layered atop traditional PV cells, they act as spectral converters, expanding the cell's effective absorption range. Similarly, perovskite materials can be chemically adjusted to capture both visible and near-infrared light, offering a cost-effective and flexible alternative to conventional panels. Another emerging strategy involves thermophotovoltaic systems, which convert heat into electricity through infrared emission. In these systems, a thermal absorber collects solar energy and re-emits it as infrared radiation. This radiation is then captured by a specially designed photovoltaic cell optimized for infrared wavelengths. Advanced TPV cells using materials like indium gallium arsenide or IG gas and gallium antimonide or GaB have demonstrated efficiencies exceeding 40% under controlled conditions. Because they can operate even after sunset by utilizing stored heat or waste thermal energy, TPV systems offer a pathway to continuous solar power generation. Recent breakthroughs in plasmonic and metamaterial engineering are also expanding the infrared frontier. These nanostructured materials manipulate light at sub-wavelength scales, concentrating and directing infrared photons toward active layers within a solar cell. Plasmonic nanoparticles, for instance, can enhance local electromagnetic fields, boosting photon absorption even in thin or low bandgap materials. Metamaterials, with their precisely designed optical properties, can trap and recycle infrared radiation that would otherwise escape, further improving efficiency. In parallel, up-conversion and down-conversion technologies aim to transform the solar spectrum itself. Up-conversion materials absorb multiple low-energy infrared photons and re-emit them as a single higher-energy visible photon that a traditional solar cell can use. Down-conversion does the opposite, splitting high-energy photons into multiple lower-energy ones to reduce losses. By integrating such materials into existing solar modules, scientists hope to surpass the fundamental efficiency limits of standard photovoltaics. The ability to harvest infrared light could dramatically reshape the global energy landscape. Infrared active panels could operate efficiently even under cloudy conditions or at night by capturing ambient thermal radiation from Earth's surface. Moreover, since infrared light is abundant in waste heat from industrial processes, hybrid solar thermal infrared systems could recover energy that is currently lost to the environment. Despite the promise, challenges remain. Infrared absorbing materials often suffer from stability issues, high production costs, or difficulties in large-scale fabrication. Ensuring compatibility with existing PV manufacturing lines is also essential for commercialization. However, rapid advances in nanofabrication, material chemistry, and photonic design are closing these gaps quickly. As the world transitions toward a clean energy future, harnessing the full solar spectrum, including the invisible infrared realm, could redefine the boundaries of solar technology. By turning previously wasted heat into usable electricity, scientists are not just improving solar panels, they are transforming the way humanity interacts with sunlight itself. The next generation of solar power may not only shine in the day, but glow from the warmth